Okay. So in order to understand what compound is being made, spectroscopy is used. And so I started recording so that I can put this on YouTube for you.
Oh, thank
Because spectroscopy is very simple. You've just got to know a few things. So this is the way I used to teach it when I taught lab. And the idea here is that each of these spectroscopies will tell you something different. You
you.
can spend a lot of time getting really good at each of these. But for your sake, as a student right now, you just need to understand what each one is going to give you, meaning don't waste more time trying to get more information out of it than
Yeah,
you can.
know the little differences pretty much.
So IR stands for infrared spectroscopy.
Hmm.
This will tell us about functional groups. We can tell if something has like a carbonyl, carbon double bond oxygen, or an alcohol, an amine. If you have carbon carbon double bonded with the hydrogen, or carbon carbon single bonded with the hydrogen.
Hmm.
We can tell just a lot of functional groups by where these things are, and we'll get into that. MS stands for mass spectrometry. You might also see it as mass spectroscopy. That's the old timey term. But
Okay.
the idea is that we are going to use this to figure out to determine the molecular weight of a compound along with the molecular weight of fragments. So imagine you have a giant compound and we can get the molecular weight from it, but imagine snapping it at certain places so we can see the weight of all of the different fragments. So we're kind of have like a little, if we connect A to B, we can get like the general thing. So we'll
Mhm.
see what that means, but basically it just breaks it. NMR stands for nuclear magnetic resonance.
Mhm.
Essentially, what this is that this is just a giant magnet. And based on a lot of very funky math that's complicated, we can tell A for H1 NMR, we can tell how many protons and what they're attached to,
Mhm.
and how many neighboring protons there are. Carbon 13 is a little simpler, but it'll tell us how many unique carbons we have. And we can figure out, is it a carbon that's only connected to other carbons? Is it a carbon that's double bonded to other carbons? Is it a carbon that's connected to things like an oxygen or nitrogen?
Mhm.
That's going to, IR and carbon 13 are going to be your simplest one. H1 proton spectroscopy takes a little bit of work, but it helps you out and it's really easy once you get used to it. Mass spec can be tricky and it just depends on what your instructor wants you to learn from it.
Okay.
Does that make sense?
Yes.
All right.
So all of these pretty much have to do with the lab, though, like the actual experimental portions of things.
Yeah. So basically, what this is going to be used for is that imagine like you have a compound and you are transforming a ketone to an alcohol,
Mhm.
right? And so there's a lot of different techniques you can use to do that. Um, and so uh, just depending on what's happening, um, you are going to use each one to figure something out. So IR can tell you if you change that functional group because what the signal for the ketone should be gone, and now you should have one for alcohol. And so
Mhm.
basically, this is what we do. We use these techniques uh, on figuring out what differences are happening. Does that make
Mhm.
sense?
Yes.
Okay. All right. All right. Let me turn the. Oh, I forgot. This is a Word document. I have to scroll down. Okay. So new drug ideas come from natural products. So, all right. So the idea here is that when we are making the different compounds, like if you want to make a new drug, a vaccine, or other stuff like that,
Mhm.
um, this is where we get ideas from. So we take inspiration from nature and biology. One of the things that I once heard
Okay.
one of my advisors tell me is that God does things really cool. So if we just kind of follow his lead, it's usually not going to be too bad. So that's the way to think about it. And so this modern drug research here, basically, I don't know if you need to know this necessarily, but the idea is that you kind of figure out what you want to work on. Meaning, do I want to find a cure for a certain type of
Yeah.
cancer or treatment? Do I want to work on an immunization for some disease? Do I want to do something for blood pressure? And so
Mhm.
once you figure out what that is, you're going to try and think, are there any drugs currently on the market that do this? Right. So if you wanted to lower cholesterol, you would look at something like Lipitor. And
Mhm.
so then you could try and build something off of Lipitor, like kind of say, well, I know that this drug does this. So you would try to figure out like also if you think about like what happens in your body, what regulates the breakdown of cholesterol, what regulates the up, and you can try and maybe think, oh, it's this molecule. Can I make a similar drug that turns on the breakdown of fats and stuff like that, which might be useful.
Okay.
And then you go through and you just basically just like try to make all these different versions of it.
Mhm.
And then once you find one that works, you do a clinical trial where basically it's 3 levels of clinical trials and you test it in small doses. So basically, you test it first to make sure it doesn't do anything bad, like
Mhm.
to humans. And then you test it to see how effective it is. And then you test it for any long term effects, kind of thing. And then once you pass all your clinical trials, you can apply for release of drug and stuff like that. And so some drugs take 10 to 15 years to develop. So some companies will start up and they will never make a profit because they try to make a drug that just they couldn't make.
Mhm.
And sometimes they make great things. So the people that made like Viagra, they're rolling in money. The people that made Lipitor, they're rolling in money just as long as you make one. Um, Natural product isolation. And so this is the idea, right? Where um, aspirin, for example, there was a tree that ancient Greeks and stuff used to chew the leaves on. I think it was Greeks. I could be wrong. And it was a way to soothe inflammation and pain.
Mhm.
And so by the time scientists came around, they went and studied it and they found like there's actually something in it that's very similar to aspirin in its composition. So they figured out how to make it. So you find these things that are natural treatments. Like when the people say they have folk remedies, there's always a little bit of to it, right? There are things that people can get. And it's like folk remedies are useful, but if I can make a much better drug that's more effective, right? Like I'll take a certain type of tea to make my stomach feel better, but I'm gonna want to have something that's like made in a lab for an immunization shot, right? Kind of like the best of both worlds. Um, do you know what uh, what's like in cayenne peppers and jalapenos? You know the active ingredient of that.
Mm-mm.
If you are to eat a pepper, um, it's got an ingredient called capsaicin, and
Mhm.
capsaicin is the active ingredient that makes things hot. Do you know what long-term condition is treated by the symptoms is treated by capsaicin? You can
No.
find creams in the medicine aisles, and they recommend that people include it in their diets, like to eat peppers and stuff like that to help them.
What is it?
Diabetes.
Really?
Yep. So what happens when you eat something spicy to you?
Mm,
Do you feel like flushed? Do you
kind
get like sweaty?
of.
It opens up your blood pathways. And so remember, a lot of diabetics have poor circulation. It improves circulation.
Wow.
So something like capsaicin that you think we've only been using it for food, this is the idea of a natural product. We can find things and think about it. So like, oh, if I eat this, this is the effect. Can we make this into an actual drug? Can we actually make it specified? So
Mhm.
capsaicin isolated and used in a cream actually helps people.
Mhm.
So this is the idea of a natural product. Also, we do this because natural products, they come from very specific things. But imagine there was a tree in Java that was a cure for uh, baldness. Like it would help if guys were going bald, right? Those trees would be gone very quickly because there's only like a finite amount of trees.
Mhm.
So this is another idea of why we make it, right? Is that if we can find something that works, then as a scientist we can make a lab copy that we can produce on a much larger scale. So one of the best examples of this is that one of the early chemists who studied hormones had to kill like 10,000 pigs just to get a gram of it. I mean, they were still butchered and the meat went to, like something like that, but they needed a particular organ. And so you can think about, wow, that's ridiculous. But then they figured out how to make it and then you could study it and do it for other things. So it wasn't like that. So,
Yeah. So we actually did do this in lab. That's what I was telling you about. Like this, we did the extraction and I forget the two other things. Oh, like separation and extraction of a natural product. Like
yep.
that's when we use this spinach, so we could like we never got to do this portion though, which is why when I was looking at this, I was confused because there wasn't enough time this semester to actually like put them in the little cuvettes and run them through and see like what products were in it. So Smith just basically told us what was in it, and he was like, "There's chlorophyll A and B and like all this
Yeah.
other list," and he showed us the graphs, but I just like I didn't really know because we didn't physically do it. He just explained to us like a little bit about this, so I do understand this.
Okay. And so basically the idea is once you identify what's in there, then you can work on trying to synthesize it.
Mhm.
All right. So as he says, the chemist's eyes, ears, and nose. Really, this is just us making sure what's in there. And like I said, each one of these tests tells us something different. And the trick, the smart chemical student like you, if they have the right teacher, and you do, because this is what I specialize in, is to teach you all of the quick tips and tricks so that you don't waste time trying to learn things you don't need to know.
Mhm.
All right. So, what is spectroscopy? So, basically, we are going to use electromagnetic radiation. We're going to shoot it at our samples. And so, basically, when we shoot it with electromagnetic radiation, depending on the frequency, which virtually relates to the energy,
Mhm.
our molecule is going to behave in different ways. So, the way that I like to think about this is imagine you, Marky, are standing in the middle of the soccer field.
Mhm.
And imagine a light wind comes. What's it going to do to you? Maybe it'll blow your hair around a little bit, right?
Yeah.
Now imagine a very strong wind comes and now it pushes you, so you kind of have to like lean into it or like take a step back because it's a strong wind. So now you're actually having to move. But imagine that someone came up and actually pushed you, right? You're going to fall down unless you brace yourself. So this is the idea of us shooting different levels of energy. We're going to have different effects on our compounds.
So that's like what's changing. It's like the
The type of wavelength we're shooting at. So like in NMR, we're shooting magnetic waves.
Mhm.
In IR, we're shooting IR waves. In mass spec, we're shooting like ionization energy. So something like very, very high energy.
Mhm.
So it just depends. And so after we do this, it's going to cause some type of change or effect or whatever. And our instrument will detect that. And it's going to produce something called the spectrum,
Mhm.
singular, or spectra, plural.
Mhm.
So basically, all it's yeah, this is wrong. It should be spectrum. Don't shame on him. Um, but essentially, whatever's in your compound is going to react in a certain way based on what type of bond it is. So that means like what type of functional group, what type
Mhm.
of hydrogens are nearby, and this is why we use different instruments, is that they tell us different things.
Mhm.
All right. So our types of spectroscopy: IR. This measures the bond vibration frequencies in the molecule and is used to determine the functional group. MS fragments the molecule and measures their mass. This can give us the molecular weight of the compound, functional groups, and fragments. So based on how things break, and we'll go over this as we get into it, we can tell like, is there a halogen? Is there an alcohol and stuff like that? And it can tell us a little bit more how the molecule is assembled. So
Mhm.
infrared kind of tells us what's there. Mass spec tells us like how is it actually built.
So um when when we use all of these, do you
Mhm.
do it all like in one experiment? Like you should do all of these types, or it depends on like what you're trying to do.
In the actual real world, so imagine like when I was in grad school and I was doing like experiments,
Mhm.
I would probably only ever use NMR because that's the most useful one.
Mhm.
But if it was like for a lab, if it was like I'm studying something about functional groups, IR might be the really quick, easy way to do it.
Okay.
And it just depends. But the more data you have, the easier it is to confirm what you have.
Mhm.
So you can think about it like, I think this is true, or this is my compound. And so then all of the spectra you produce has to match. Like you can't find a discrepancy.
Mhm.
And then ultraviolet, this will tell you bonding patterns. We use that like when we talk about like if we have a conjugated pi systems, like, alternating double bonds or something like that, that's what UV spec is useful. Okay, so wavelength and frequency. And of course, the higher the frequency, right? The higher the energy, the lower so wavelength and frequency are inversely proportional.
Mhm.
So as wavelength increases, frequency decreases and vice versa. And then, all right, so these three equations, make sure you know. So the speed of light, since light travels in a vacuum, equals lambda nu. So that's the wavelength of light times the frequency will always equal the speed of light.
Okay. So is
Um,
this unit kind of just gonna be like math?
no,
Oh,
I wish.
oh,
It's interpretation.
so it's
But I'm
more.
going to teach you all of the easy things to do.
Okay.
So know then that so now we see that lambda equals c divided by nu,
Mhm.
or nu equals c divided by lambda, right? So if you look down there, right, we have E equals h nu, and nu is our frequency.
Mhm.
H is Planck's constant. So here's the thing: if they ever gave you a problem that said, here's the wavelength of light, um, what's the energy of this wavelength, right?
Mhm.
Some people like to do this nonsense, which just seems ridiculous to me. So they'll say, well, um, nu equals c divided by wavelength. So they'll plug in the wavelength and divide the speed of light by it, and they'll get this, and then they'll put it into this equation. But that just seems very long way to do it.
Mhm.
So what you can do is, if they ever ask you what the energy of a photon is, and they give you the if they give you the frequency, that's just this right here. So you don't have to do anything to change it. But if they give you the wavelength, then you can do E equals hc divided by wavelength. So Planck's constant times the speed of light divided by the wavelength.
Okay.
And this is an easy way to do this.
Mhm. So it's just like a simple conversion question, pretty much.
Mm-hmm. Just
Okay.
to make sure, if you use this, I don't know why. Okay, this is bothering me and this is bothering me, but just use those. I won't get involved with that.
Okay.
I hate your teacher just ever so slightly.
Me too, but it's not ever so slightly. Person, amazing person, professor. I I feel bad because like we had to write the reviews, and I was like, and this class was difficult. Um, and he said like give him one thing he did well and two critiques. And so literally my critique was just like for people who don't understand chemistry very well or like have a hard time relating. Um, one thing I would suggest is like trying to find simpler ways to relate it for those people. Because like our averages have been terrible this whole semester. And he literally told us that our last quiz, the one we took a couple weeks ago, he's like, this is the lowest you guys have done all semester. And we're just like, we're getting worse. Like, we're supposed to be getting better, but we're getting worse.
Yeah,
And
that's
then
not
and
ideal.
he literally was like, I'm not rounding you guys because you have to know these for OChem 2. And like it's like a form of like you guys better wake up and learn these cuz I know all of those ones that you did with me, we have to know them again in the beginning of OChem 2.
Mm-hmm.
So like make sure you stay up on them, but at the same time it's like okay, maybe we needed more time or something cuz nobody did good on it. Like nobody did how they wanted to do.
Yeah.
So,
All right. So here's our EM spectrum. Uh, you should know radio, microwave, IR, visible, UV, X-ray, gamma.
okay.
So don't forget higher energy, higher frequency, shorter wavelength,
Mhm.
and then vice versa. So IR region. So IR region is wavelength is slightly larger. It's less energetic than the visible region, so the energy is not as bad.
Mhm.
And so we see that in the units for IR spectroscopy is something called wave numbers, or basically centimeters to the negative one. So it would be 1 divided by a centimeter.
Okay, yeah.
All right. So basically, this is lower energy, so it doesn't do too much. But what this does is this right here called something called molecular vibrations. So you can see here that imagine our atoms are two balls, and then our bond is a spring between them.
Mhm.
So you can imagine that we have this at their normal bond length, and then they stretch and compress. And so this is our quick like representation. And so if we put energy in them, we can cause our bonds to express and contract. But
Mhm.
we think about equilibrium bond length, and that's the ideal bond length that we have for atoms. And so if we put energy in IR energy, it'll cause them to do that. And so basically, you can think of an IR as shooting an energy at different wavelengths.
Mhm.
And so, based on what type of bond it is, once you get to the right energy level, it'll cause the bond to vibrate.
And that's like when you know it's at equilibrium.
That's when you know that it's there.
That's when you know it's there. Okay.
So basically, we know that basically the vibrations are going to happen. It's going to be at equilibrium bond length, but once we hit it with the right energy, it's going to start contracting and expanding.
Okay.
Because you can imagine that it takes so much energy to like compress or expand a spring. It's the same idea. So as we go from different wavelengths of light, there's going to be more energy, right? And so if
Yeah.
we get to the right level of energy, then it can do that.
Okay.
So here is the math, and I'm not sure if you're going to need to know this or not, because this is, to me, pretty ridiculous, but this is just an equation you can plug in, and this is to know the frequency based on what's happening here.
Okay. If I see it on the review, I'll just go back to this because I don't. If there's an equation, I can do it because I feel fine with the math. That's just like the other stuff.
Yeah.
But
So you can see here that our bond strength, so you see we go from single, double, and triple, right? Bond order increases. You can see that the frequency increases because it takes more and more energy to do it. Because don't forget, this is the inverse. So,
yeah.
But basically, this is just the idea. And so this is why, based on where that wave number is at, if we look at our spectra, a spectra for IR goes from about 400 up to 4,000. And so you could see if you saw a carbon-carbon single bond, it would pop up at 1,000 wave numbers. A carbon double bonded to carbon would pop up around 1,600, and a carbon triple bonded to carbon would pop up around 2,200. Does that make sense?
And the wave numbers are the.
It's basically the wavelengths, just one divided by the wavelength.
Okay.
And you'll see it when we get to the spectra. So basically, no two molecules will ever give you the same IR unless they're enantiomers. And so this is a big thing. The fingerprint region, when we're looking at anything between 6 and 1400, so basically the far right of our spectra, ignore it. You'll never be able to pull anything out because it's just so complicated. So many things are happening there.
Okay.
So when we actually look at the spectra, we're going to get most of our stuff out between 1600 and 3500.
Okay.
It'll make sense once you see the spectra, and I'm surprised it hasn't
all
shown
about
you.
the functional groups.
Here you go.
Okay.
So now you can see that single bonds pop up right near the fingerprint region, but then as we move out, we get double bond stuff, we get triple bond, and then we get bonds to hydrogen. So based on what's happening, this is basically where we're going to see things depending on certain things.
Okay.
But again, the important thing is that there are so many values you can find on an IR table looking at when you're looking at this, and it's very easy to get blinded or confused by everything, but you don't want to do that. You just want to pull out what you need to know. So the way that I tell my students to solve these problems is because you'll be given spectra and you have to figure out what the unknown compound is.
Yeah, so that's what I was going to ask you, like, how would we get asked this on a test?
Here's an IR, an NMR carbon, NMR proton, and a mass spec. What's the compound?
Okay.
But the way I tell my kids to think about it is it's like a jigsaw puzzle. Every type of little test is going to tell you something different. The key is to know what you can get out quickly. So it's kind of like you're trying to figure out what your pieces are.
Yeah.
And then once you figure out what all of the pieces are, then you're just going to like take and try and connect them to get the right shape. Like you may see, I know I have an OH and I know I have a bromine. I have a CH2, CH3, and then you just will try to connect all of those pieces to get everything you need. Like it'll make sense as we go through. All right, so here's a table of all of the things I guess he wants you to know. It's a lot, but don't worry about it. There are some, and so here is, oh goodness. So here's an even more complicated one. So you see the wave number? It goes from right to left. So when you get to 1400, we generally don't look over here to the right unless you're actually in. I took a spectroscopy class in grad school, and it was probably one of the most horrifying classes I've ever taken. But
take a spectroscopy class?
It was a graduate level class. Like it was rough. But the idea here is that we can see a lot of things in this, and it's very easy to get lost unless you just know what to look for. Meaning, there are some things that take a little bit of time to say, I think this could be this might be this functional group. So, for example, right, can you see here? I have my mouse over benzenes,
Mm-hmm.
alcohols, and stuff like that. So, you have carbon carbon double bonds. So, you could have a lot of things that are just overlapped with each other, right?
Yeah.
And so, the key thing is that you've got to know what to look for, what you're going to pull out. Like, don't try to pull out everything, just pull out the things that you can pull out quickly.
Okay.
Like, um, for example, imagine you and I are sitting outside eating the Chick-fil-A, right? And we're sitting someplace where we can see traffic go by on Camelback.
Mm-hmm.
And now a car goes by, and I know that it is a Lamborghini Diablo. All right. I know that just from personal history. You may look at it and say, that's a car. It looks really nice. It looks pricey, but you don't know anything else more than that, right?
Mm-hmm.
And sometimes that's the way you've got to treat it is I know this general thing is there. I'm not going to try to pull out any more information.
Okay.
And this is like, it's just really, you're going to see some common things that you need to see. And I'll see what he has on these next few slides. All right. This is your FTIR spectrometer. So basically the way this works, essentially what you're doing is you're shooting in a light into your sample
Mm-hmm.
and it gets split. So light splits. I don't know how much you know about light as a principle.
Not a lot.
Basically what happens is that you see here it gets split. So one goes to a mirror like
Mm-hmm.
this, and then it comes back down, and then it's going to go into your sample. And so based on how that light interacts with your sample, it's going to tell you where the absorbance is. Basically, light's going to be absorbed by vibrational stuff.
Mm-hmm.
Right. And so here's your IR spectrum. Each stretching and bending vibration occurs with the characteristic frequency as the atom's charge. So basically, like we said, depending on the energy you're putting into it, it's going to cause things to vibrate. And so depending on where it's vibrating will tell you what functional group it is or what type of bond it is.
Mm-hmm.
So here's your IR spectrum. So for example, you can see here that 1400 is right here.
Mm-hmm.
So everything to the right, we ignore.
Okay.
But now I have this peak at like 15, just south of 1500. I have these peaks around 3000, and each of these tell me a story.
Mm-hmm.
And basically what we're going to do is just, we want to figure out what each of these are. So I know that these peaks here are carbon-carbon carbon single bonded with hydrogens.
Mm-hmm.
But that's it. That's all I can see from this. I can't see anything else. And so as we go through, here's IR for alkanes. So this is where you see alkanes. So alkanes generally are useless for you unless it's a carbon attached to a hydrogen. And we see those peaks just below 3000. So sp3 carbon hydrogen bonds are between 2800 and 3000.
So basically, I just memorized these values on this thing.
The bottom one, don't worry about the other ones.
Okay.
Because the other three are well into the fingerprint range or right at the border, so they're not going to tell you much. They're going to be hard to pick out sometimes.
Okay, so basically, it'll be more of like what we saw on the last slide, and it could have like a circle around it or something and be like, what is right here? Like that could be a thing.
Yeah.
And then, okay. Okay, well, that makes sense.
Right.
I had a question on the absorbance too, because I never really understood this. If there's more absorbance, like what does that mean? Why is that so like, oh, this?
Oh, okay. Well, there's two ways that this could work. Imagine, what is light comprised of? Photons, right?
Yeah.
So imagine I have a light on one side of an empty room and a detector on the other side of the other room.
Mm-hmm.
So I turn my light on and my million photons go across this space.
Mm-hmm.
Now, say all 1 million get there. I will say that I had 100% transmittance, meaning that I transmitted all the photons from where I started to where I ended.
Mm-hmm.
What's my absorbance? Do you think?
Is it also 100?
0.
0. So it's the opposite.
They have to add up to 100.
So
Because absorbance means how much does a molecule absorb?
So when it's going from one place to another, is the absorbance not like when it gets to the destination? That's the transmittance.
So basically, no, all right. So transmittance is how much of your original light source reaches the detector.
Okay.
Absorbance is how much light was absorbed by your sample.
Okay. Okay. Yeah, that makes sense.
And so they have to add up to 100%.
If more is absorbed, then less made it to the detector.
Correct.
Okay, I got it.
And so the way we can think about that is that either it's the right type of bond that's really good at like the whatever light's hitting it, that bond can absorb the light very easily.
Mhm.
Or we have more of what's in there. So like the light will hit more things as it covers through the solution.
Okay.
Does that make sense?
Yeah.
Okay. So here, right, we have this wonderful compound, 1-octene, and you can see that carbon-carbon double bonded is about right here. This is at about 16 to 1700, right?
Mm-hmm.
And then the carbon double bond, the sp2 carbon hydrogen bond is right above 3000.
Mm-hmm.
So this is one of the most important things that we'll go through, and I'll give you a simple list at the end of this, but this is just another idea of you simply saying, this is how you look at it. And then we have things like alkynes, where you'll see if it's a terminal, if you'll see the carbon-carbon, this is pretty unique because you see it at about 100. It's just this small little peak about midway down, quarter of the way down.
Mm-hmm.
And then you have this, if it's a carbon, like if you have an H attached to that carbon-carbon, sp,
Mm-hmm.
it's a very, very strong peak at about 3300. And so we're going to say that it's a strong peak if it goes all the way down, it's a medium peak if it goes about halfway, and it's a weak peak if it barely comes down.
Okay. So each of these that we're going to be going through, these are the ones I need to really know.
Most likely.
Okay.
Yep. And then you have like your carbon-carbon double bonds from things like benzene. And then you have ethers. And again, if you look at ether, it's down in that fingerprint range, right?
Mm-hmm.
So that doesn't help you at all.
Mm-hmm.
So some things like ethers are pretty much useless because they just will not help you at all.
So you know how like just some of these are highlighted, like some regions? What about like the other ones? So we have like the blue on this one. What about like the one directly next to it and it's like going further down?
So this peak, if you remember right below 3000, is the carbon, the sp3 carbon hydrogen. So the hydrogen's coming off of here, 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 and here. That's what these peaks are.
Oh, okay. I'm starting to get it. So it's just like, even though that's just like one of the things, like it's present, but we're more focused on like the first two regions because those are like
Correct.
Okay.
I need to grab a Coke real quick because I'm running out of steam. So 1 second.
Okay.
I'm going to hit pause real quick on our record because you don't need to see me do that.
It kind of makes me feel better that a lot of other people feel the same way as me in the class.
Mm-hmm.
So it kind of lets me know, like, okay, my classmates also feel stressed, and like they're not understanding it either.
Mm-hmm.
But it's weird because I feel so good, and then I go to the test, and it's like, I don't know.
Markie, you bested the average by 30 points.
Yeah.
You're not a chemist, but you're still outperforming an entire room full of them.
Yeah. There's always like those two people that get really good grades, like 100.
Those are probably chemists that like, I got 100s when I took that class, but that's just because I get it. Like that's just my thing.
Yeah, I know. And my physics final, it's 2 parts on Tuesday and Thursday, but it's open note, open book. It's just like no Google, like no internet, but you can use like any resources because it's like we have to do it at home and they're basically like math is math, and we gave you guys an equation sheet anyway. So like if you were in school, you would use an equation sheet. And last year they let people take it like with partners and stuff. So it's like, I don't know.
Are you going to choose me to be your partner?
Possibly. I mean, it's on Tuesday and Thursday, so I have all day to take it. I might phone a friend.
Tuesday would be fine as long as it's in the afternoon. Thursday would be fine anytime.
Honestly, if you don't mind just like being on there with me while I take it, because
Mhm.
I also have a B in there and I really want to get it up to an A. I have to get like an 85 on my final.
I'll
In order
say anytime after 3 o'clock your time, both days.
Okay. Thank you. I meant to
Mm-hmm.
ask you that earlier, but I was thinking, I was like, well, if it's open note, like that technically, he's technically a friend. And my mom was like, oh, Jesus, here we go. But because I've been studying for this, like, it's just, I don't know. I think I'll be okay. But
No,
I have a little panic on my lab thing. And then I figured it out. Oh, God.
I mean, in reality, even when we've done those like things, it's really just you talking to me and making sure that your line of reasoning is makes sense. You're not like having me do the work for you.
Yeah.
Okay. So here's something really weird. It's blue on the chart, but it's yellow up there. It should be blue.
Okay.
So what do you notice about the OH peak that's blue?
But it's like the region of it, or it's bigger, it's wider.
Yep. So that BR stands for broad.
Oh. Okay.
The S to the right by the red one
Mm-hmm.
stands for sharp.
Sharp.
So it's basically
So,
just how wide the peak is. And depending on how wide the peak is, will tell you what it is.
so you know how this one's like in that specific region too, but it's broad?
Mm-hmm.
It's the OH is always in that region,
Correct. You will always see a peak like that for an alcohol.
but does it have to be in that region?
Yes, it has to. Because remember, we
Okay, so
said
if a broad
it
one somewhere else, it's not OH, it's something else.
correct. Because remember, we said depending on what it's connected to, when we hit it with the energy, it's going to vibrate in a certain way. So
Mm-hmm.
because we need to have an oxygen attached to a hydrogen, you're
So
going
like,
to always fall into that region. Even if you had something like a carboxylic acid, which is a carbon double bonded to oxygen and then single bonded to the OH, you'll still see that broad peak.
okay.
But this is basically it, is that now you're starting to get it, right?
Mm-hmm.
So OH is one of the easiest things to see, and that's one of the things you should definitely commit to your memory because that is so easy to see.
Mm-hmm.
This is why I'm saying there are some functional groups it pays to pay attention to because they pop so easily.
Mm-hmm.
All right. Here we have an amine.
Okay.
And so
So
if you notice,
green.
that's the carbon and nitrogen.
Okay.
Good job there. What's his name?
Who knows what his name is? Just kidding. Gosh. Ron.
Ron. Good job there, Ron. So basically, if you notice, how many hydrogens does my nitrogen have?
2.
What do you notice about the peak?
Is 2.
Mm-hmm. What would you expect a secondary amine to be different? Same region, probably.
Yes, but not as many. Or
Yep, it would just have one peak.
yeah. Oh. Okay,
If
it's
it's a
still not that bad.
if it's a tertiary amine, there'll be nothing there because there are no nitrogen hydrogen bonds.
So this is like, I'm just trying to think. This is it only gonna ask like the regions, and then I would just say like amine, or do I have to like name it like this thing?
Oh, okay, no. So that's a compound. Remember, what did I say to treat this as?
A
It's a
puzzle.
puzzle. You're pulling
So,
pieces of
okay.
information out. So you
Find a
made
compound.
you can't know that it's pyridine just by looking at this unless you memorize the IR. But
which I'm not going to do.
if you remember, you have something right below 3,000 to 2,800.
Mm-hmm.
Do you remember what that was?
H.
What type of H? sp3 carbon hydrogen.
sp3. Yeah. Okay.
So if you look here, sp3 carbon with hydrogens, sp3, sp3, sp3.
Mm-hmm.
This won't tell you anything about the structure outside of what there is at a basic.
So since it's multiple choice, do you think he'll show us the structures? Because obviously, well, I guess I could draw it based off the name. So never mind.
Yes, but don't forget, this is just one part of what you're learning about.
Yeah.
The other ones are going to tell you information. So you can imagine again, Marky, you and I are eating Chick-fil-A and we see a Lamborghini Diablo go by.
Mm-hmm.
Me loving the car, I could explain a lot of things to you about it. But I said, Marky, could you tell me what is in that car? What would you tell me? What would you know about that, it being a car?
A steering wheel.
Yeah.
And a gas pedal and a brake.
Yeah, there's a seat. Probably like you would tell me things. This is what IR does. It tells you things that are there. You just don't know exactly where.
Mm-hmm.
You just know that it has an OH. There is a carbon double bonded to oxygen. It
So
has sp2.
the first piece of like the whole process.
Mm-hmm.
You know what it is. Okay.
When you're looking at an IR, you should never spend more than a minute on it. Get everything you can from it as quickly as you can see. So things like an alcohol, things like an amine, other than we're going to see some probably other functional groups. They pop very clearly, right? And so here is the terms you need to see.
Mm-hmm.
So. And this is just the idea of, this is just some basic terminology. And as you practice, you'll get better at it.
Okay.
All right. Look at that yellow peak.
Okay. It has like a line coming down too.
It's a very, very sharp one.
Mm-hmm.
So anytime you have a carbon double bonded to oxygen, you're always going to see a sharp peak between 1650 and 1800. Doesn't matter if it's a ketone, aldehyde, carboxylic acid, amide, acid anhydride. It doesn't matter. If it's a carbon double bonded to oxygen, you're going to see that peak. It's just going to be shifted depending on what it is. But if you notice here, a unique thing for carbon, for our aldehyde, is that you're going to see a peak, a doublet at 2780 and 2820. So these two peaks right here, that's from the carbon hydrogen.
Mm-hmm.
And then this right here tells you, so this tells you that there's carbon double bonded to oxygen. If you see this weird little doublet here, then you can be like, then I know it's an aldehyde.
Mm-hmm. Okay.
Are you eating your sunflower seeds?
Mm-hmm.
Me too.
Cheers.
Yeah. Not your sweet and sour ones, but
Uh-huh.
what's the expiration date on those?
What?
What's the expiration date on those? I'm curious. It should be on the backside by like the little barcode.
Best by March 3rd, 2021.
Okay. But that was made recent.
I did not know these are gluten-free.
Well, yeah, why wouldn't it be?
Because I feel like gluten's in a lot of stuff. I'll have to tell Eden she could have these, my friend. She thinks she can eat anything.
Gluten's only found in like processed like wheat and stuff like that.
And pasta.
But what's pasta made out of? Wheat. So just think, if it's a carb, it might have gluten in it.
Interesting.
Breads, pastas, right?
I could never be gluten-free.
Yep, neither could I.
I think I would eat it anyway.
It's like when people are like, I like vegetarian. I don't think I ever could because I really like meat.
Mm-hmm.
I know I can have vegetarian meals, but like if I had to go vegetarian for a little bit, I probably could, but I don't think I could do it forever.
There's
Um, but when I hear people say they're vegan, I'm like, no, because that means no dairy, and that's not a life I want to live. Uh, when we're done recording this, remind me to tell you the story about the date with the vegetarian.
okay.
So that carbon double bond to oxygen is going to be one of the easy ones, like the alcohol you can pull out. It's really easy to see. All right. So now instead of an aldehyde, we have a ketone.
Mm-hmm.
And again, we still see that very sharp peak.
How can you tell the difference of when it's Oh no, never mind. I got it.
Now, if we have an ester, peak is a little closer to 1800,
Mm-hmm.
but we have another peak, but it's in the fingerprint region, so we don't see that one all the time. But as we said, when we go through this and we start looking at the other things like the NMR and all that stuff, the fact that we have that double bonded O tells us that there has to be some type of carbon double bonded to oxygen. Maybe it's a ketone. It's not an aldehyde, right? Because we don't have that weird doublet that we saw.
Yeah.
If you had a carboxylic acid, you would see a big OH peak over here.
Mm-hmm.
So because we don't see some of these things, this is what tells us it's maybe an ester, maybe a ketone, and it just comes with practice. But again, you being the smart person says, I know there's a carbon double bonded oxygen, not an aldehyde, not a carboxylic acid. Just keep that in mind.
Okay.
All right. And then here, there you go. See, look, carboxylic acid.
Mm-hmm.
All right. Acid anhydride, we see two sharp peaks around 1700.
Mm-hmm.
Amide, we see that sharp peak again, but now we're going to see two peaks over here like we saw with the amines, remember?
Yeah.
Carbon double bond to nitrogen or triple bond to nitrogen is around 2200. It's a very sharp peak, it goes all the way down.
Mm-hmm.
All right, so now conjugation. So conjugation, basically, like if we have a conjugated system, it will cause our peak to go further to the right.
Okay.
So if you look here, we have a ketone that's not conjugated with the ring because there's an sp3 carbon in the middle.
Mm-hmm.
And that's at 1715. That's about where we normally expect to find ketones. If it's conjugated with the ring, now it's at 1684. We moved it to the right.
Okay, I see.
Oh. And we're going to see this trend no matter what we're doing. If it's conjugation, to always move the value to the right of where we would normally expect it. So if we're expected to see something like at 2000, it might be like at 2150 or something like that. Everything's just going to go gently to the right.
So basically all of these just like there's gonna be a couple things that are similar and you have to spot the difference and that's what determines the functional group.
Yes.
Like
But
there's
like
this,
I said,
it's not this, so it's not that. And then there's this, but it's not that.
and like I said, though, a lot of times you're not going to get stuck trying to figure out exactly what it is. You just want to pull out a simple, it could be this, and then you'll move on to the other spectroscopies and get more and more information from them. If that makes sense.
You got it. Oh, thank God, we're at the last one.
So again, you can see that when we do the conjugation, it lowers our carbon double bonded to carbon because originally it was at 1660, but then as we add conjugation, it moves it closer to 1600.
Mm-hmm.
And that's it. Well, this is a really hard one to see, so you necessarily won't pay too much attention to it.
I'm gonna see how much is on there.
Does that make sense?
Yeah, this wasn't too bad. I'll just review this tomorrow.
Mhm.
The next one's